Hello and welcome to a new session for this online course on Introduction to Embedded System Design. I am your instructor Dhananjay Gadre, and in this session we are going to talk about another important aspect of embedded system, that is the ability to read external analog voltages. And to be able to do that, we need to have the support of a peripheral which is often available on most modern microcontrollers, that is the analog to digital converter. Now, why do we need ADCs? ADC means analog to digital converter. Why do we need them? We need them because the world is analog, which means the values that surround us, the features that are around us, they are all changing their parameters continuously. They can take any arbitrary value. Information like temperature or pressure or distance or light intensity, as we have seen, they are all continuous in nature. And so, we need to convert that continuous voltage, continuous parameter into discrete numbers, discrete values. Examples of sensors which provide continuous values are for using a potentiometer or a light dependent resistor or a negative temperature coefficient thermistor, load cell, a microphone, there are so many. Now, problem is that the CPU cannot read analog values, it can only accept digital numbers, zeros and ones. And so, we need a mechanism to convert these analog inputs in a digital value, and that is where an ADC comes into use. So, that is the justification for having an analog to digital converter mechanism connected to the microcontroller. This is how ADC works. You have the analog signal in the form of the output of a particular sensor or voltage. You need to sample it, that is, you decide at what point of time you want to look at this value. Now, the input is asynchronous, meaning it can change whenever it wants to. But while the conversion process from the analog voltage into a digital number is in process, you do not want the input voltage to change. So, you include a circuit which can hold the value of the analog voltage to a fixed value, to that value when you start the conversion, and hold it till the conversion is over. Such a circuit is called a sample and hold circuit. Then once you have started the conversion and you convert it, you quantize it into a discrete number and then you encode it, meaning assign a digital code to this quantized number, and once that is done, the analog voltage which started from here is available as a digital signal, ready for the microcontroller to be processed or stored or whatever else you would want to do. Here is a sample and hold circuit. You have an analog input, you can pass it through a operational amplifier which provides very high input impedance. Using a switch, when the switch is closed, it will charge this capacitor, but when you open the switch, the capacitor will hold to the value to which it was charged, and as long as the input impedance of the subsequent amplifier is very high, the capacitor is not going to discharge. Therefore, it will hold the analog voltage to a fixed state, fixed value for the ADC to complete its function. Quantization, this is the next important step. After the sample and hold process which we have seen, the signal becomes discrete in time, meaning it is being held to a value, but it is still continuous in amplitude, meaning the value could have been any value in the range that is acceptable. You need to have a reference voltage against which this analog voltage will be compared and will be divided in small discrete steps, and from there on it will be converted into a number. This is where the encoding comes into picture, the process of assigning a binary code. Do you want it to be linearly converted, or do you want to have a nonlinear function, or do you want to have a 2's complement? All this you can include in the encoding function of the ADC. There are many types of ADCs, depends on the kind of function that you want to perform, that is the kind of input that you have, the kind of speed that you want with the ADC, because ADC is not a very fast process. It takes some time for the sample and hold and rest of the circuitry to operate, and therefore, each type of ADC has a specific application. The simplest of ADC is called a counter ADC, counter type of ADC, which uses a counter and a comparator to convert the analog voltage into a number. The most common ADC is called successive approximation type of ADC, and the ADC that we have on MSP 430 is actually a successive approximation type of ADC, SAR. Then we have a dual slope, it also is a counter type, except now you use two slopes, one where you are charging the voltage to the input value, and then from the input value you discharge to a known reference value. Then you have very fast ADCs of the type called flash ADCs. In fact, the most common use of ADCs that you would notice in your engineering life would be in the use of a digital storage oscilloscope. A DSO is a digital device, but the voltages that it is able to sample are analog in nature, and therefore, at the front end, after you have your amplifiers, you have ADC, and the ADC you have in these DSO is of the type called flash ADC. The reason why they are called flash is because they are very fast, but because they are very fast, the kind of fastness comes from the architecture of these ADCs. They consume a lot of power, and usually these ADCs are offer a resolution from 8 to 10 bits, but they offer blistering speeds. For example, if you looked at the front panel of your DSO, it would say, for example, the one we have in our lab says 1 GSPS. This stands for 1 giga samples per second. This is the kind of ADC that we have on these modern digital storage oscilloscopes. And then the next type of ADCs that we have are called sigma delta type of ADC. They are used in voice encoding. So, these are the various types, but since our microcontroller is a general purpose microcontroller, is not specifically useful for high speed conversions, the ADC that it has is a SAR type of ADC. So, we are going to look at ADC in this context. This is a ADC where you do a binary search, compare analog voltage that is applied to the ADC with a binary, with a voltage generated through a binary number, and when the number matches, then you stop the conversion. You can go through this slide to understand the entire conversion process. This is the block diagram of the SAR type of ADC. SAR type of ADC requires a clock, so you need to decide what kind of clock source are you going to use. In our MSP 430 ADC, we have options of lot of clock sources. You also need a reference voltage against which the values will be compared in this comparator. Here is the input voltage held to a value using the sample and hold circuit, and when that value matches, then you stop the conversion. Now, these are the features of ADC on MSP 430. We call it ADC 10. The reason is that the resolution of ADC is a 10 bit resolution, which means from the entire range of input voltages that it can accept, the range is divided in 10 bits, and therefore, the number of levels that you have from the minimum to maximum is 2 raised to power 10, which is 1024 discrete values. The ADC on MSP 430 offers quite a fast conversion speed, and these conversion speeds are up to 200 kilosamples per second. Of course, this is very small compared to the ADCs that are available in digital storage oscilloscopes. As I mentioned, they offer speeds up to 1 gigasamples or even more gigasamples per second. The module implements a 10 bit SAR, and it has a mechanism to select the input channel, because in this case you do not have multiple ADCs on your microcontroller. You have only one ADC, but you have an analog multiplexer which allows you to select a particular source of voltage through the analog multiplexer and use the common ADC feature to convert that voltage, and then you can change the multiplexer and convert another voltage. The converted value is handled by a data transfer controller called DTC. The DTC allows the samples to be converted and stored anywhere in the memory without the CPU intervention. So, your program simply instructs the ADC which channel do you want to convert and where do you want to store the results. The DTC will take care of it. You can do up to 8 external input channels. You can convert voltages on 8 external inputs, of course not simultaneously, but in a sequential or serial fashion. You can through software select the reference voltage. The MSP430 microcontroller offers on chip reference voltage, which you can select to be of 1.5 volts or 2.5 volts, or if you want, you have a special requirement, you can provide external voltage reference also through a available pin. And the ADC core, that is the peripheral which controls the ADC, and the reference voltage can be powered down, meaning you can enter a low power mode so that these peripheral devices do not consume power. Here is the block diagram of the ADC. This is the core part of the ADC here. This is the actual converter. Here is the analog multiplexer that allows you to select so many input channels. Here is the part which allows you to select the reference voltage. You can have an internal reference voltage of 1.5 or 2.5 volts. You can have internal, interestingly, MSP430 has an internal temperature sensor, and the output of the temperature sensor can also be routed through the multiplexer into the ADC, so that you can determine the temperature of the microcontroller, the temperature of the chip of the microcontroller, and you can also have read the voltage through a voltage divider here. Now, once the ADC converts the value, it is sent to this ADC10 memory, from where it can decide to send it to appropriate memory location, so that the processor can implement a new conversion. So, this is the basic block diagram of the ADC that we have on MSP430. The ADC core converts analog voltages using a 10-bit representation. The reference voltage, as we have discussed, can be selected by the user. The digital output full scale is when the input is higher or equal to the positive reference voltage, and is 0 when it is equal to or less than the negative reference voltage. In this case, it is 0. The conversion formula for the binary format of the number is this, that is the n bits that you will get, the value of the 10 bits that you will get will be represented by this information. Here is your input voltage, and here is the reference voltage with which it is being compared. The clock, that is the rate at which the comparison will be made in the successive approximation register module of the ADC, the clock source can be selected from a variety of sources, and this is available through this register, through these bits, and the sources could be SM clock or M clock or A clock, and you could also have an internal dedicated oscillator called ADC10 oscillator. The ADC on MSP430 offers multiple ways of conversion. One of them is that you can do a single channel conversion, or you can do sequence of channels, meaning you can do channel 1, 2, 3, 1, 2, 3 like that. You could repeat a single channel, that is selected channel you can have continuous conversion, or the sequence of channels you can do repeat of conversions on those sequence of channels. These are the registers associated with the 10-bit ADC. You have the control register 0, which selects the reference voltage, the sample time, and it also allows you to generate interrupts once the conversion is over, so that your microcontroller can keep on doing something and whenever a conversion on the selected channel is complete, the microcontroller, the ADC module will tell the microcontroller that the conversion is complete. Please look at the numbers and do whatever you want with it. You have another control register 1 which selects the input channel, the format of the output data, the clock source and the divider. Then you have the analog ADC 10 analog enable control register 0, which is used to select analog inputs A0 to A7, and control register 1 which allows you to select inputs A12 to A15, and this is only available for devices which have those additional pins. Then you have ADC 10 mem register which allows you to store the result in binary or 2's complement format as selected in the control register. This ADC 10 DTC 0 is data transfer control register 0, which selects the mode of the conversion control, the transfer control. ADC 10 DTC 1 selects the DTC transfer, whether it defines the number of transfer in each block. And then the start register, once you have start register address, once you have started the conversion and you want to convert a whole set of numbers, where do you want to store them? Because if you overwrite a memory location, then there is no point in having a series of conversions. So you can define the start address and it will convert the first value and store it at the start address and the next address and so on. These are the registers and the memory locations, and I strongly recommend that you go through these slides so that you understand this is nothing but a repeat of what I have just gone through. Now what we are going to do is we are going to look at a few exercises so that you can get familiar with the whole process of initializing the ADC, selecting an appropriate channel, selecting the clock for the conversion, and once the result is available, what do you want to do with that result? Do you want to store it in the memory location, or do you want to send it to some output port, or change the duty cycle of a timer for that matter? So we are going to look at some examples. So in the first example, code example, we are going to read the analog voltage connected using this mechanism, where we have connected a potentiometer, and the center tap of the potentiometer we have connected to P1.0. We will ensure that P1.0 becomes an ADC input, and the result of the ADC will be used to send to LED connected to P1.6. Remember P1.6. So this is what the definitions are. You have decided that you are going to connect a green LED to bit 6. You are going to have ADC on bit 0. Then we have a map function. I am going to come to this later. Here are the register settings for ADC 0. What are we going to do? We are going to use P1.0 for ADC input, and we are going to use VCC as a reference, and we are going to use 64 clock cycles for sample and hold. This allows the values to be stabilized. Then for the timer 0, we are going to connect the timer output to P1.6, and we have selected P1.6 as output, and we have selected it to be timer output. And we have CCR0. You may recall that in our previous discussions we discussed that CCR0 decides the resolution and the time period of the PWM signal. So we have decided CCR0 value to be 255, which means we have chosen 8-bit ADC, 8-bit PWM. We are choosing the output mode to be output 7, which means PWM output, and the initial value of CCR1 is 1, and the clock source of the timer is going to be SM clock, and it is going to operate the timer in the up count mode. Here is the main code. As usual, we have stopped the watchdog timer, and we have called this function for register setting for the ADC, and register setting for the timer 0, and then we simply enter a infinite loop in which we read the value of the ADC, and once the ADC tells that it has completed the conversion, we simply call this map function. Now the ADC result is a 10-bit value, but our PWM requirement is 8 bits. So you have to map 10 bits to 8 bits. Instead of doing the bits yourself, we call this map function. So basically it does 0 to 1023 value, the output of the 8-bit 10-bit ADC will be mapped to 0 to 255. And the best way to think of it is, imagine that out of those 10 bits, the least 2 bits are thrown off. That is how you can map very easily a 10-bit number into a 8-bit output. And so what you should see when you compile and load this code into your lunchbox. Let me correct myself here. The LED is connected to P1.6, which, as you recall in our previous exercise, is not a onboard LED. Onboard LED is on a different pin. Here an onboard LED is on a pin which does not have a PWM function. We have connected the LED to P1.6, which is connected here. So you need a breadboard to connect the LED. Here is another breadboard connection which allows you to connect a potentiometer to appropriate pin, as discussed earlier, to the ADC input. Now when you move the potentiometer from minimum to maximum, you should see that the LED intensity goes from off to fully lit condition, and you will see that the intensity of the LED can be changed by changing the potentiometer setting. So this is the objective of the code. I strongly recommend that you download this code, build it, and send this code into the memory of lunchbox and make this connection on your breadboard to see the impact. Now we have another variation of the same code. Not much is changing here, except instead of modulating the PWM duty cycle, we are just printing the value as read by the ADC and printing it on our LCD. We already covered LCD, so you know how LCD can be connected to MSP430 lunchbox. In this case, the ADC is still connected to P1.0. These are the same connections that we considered last time when we were talking about the LCD. So those connections remain the same. Here is the code. I am not going to go through that code. This is nothing but a mix of code for the previous exercise of reading the ADC value of the connected to the potentiometer and changing the duty cycle. Instead of changing the duty cycle now, we are outputting a number onto the LCD. Here is the display that you see. It has been converted into a voltage. Instead of a binary number, it has been converted to a voltage. So you should see the voltage going from 0 to 3.3 volts, because we have chosen the reference to be 3.3 volts, which is the power supply voltage. Now in the block diagram of the ADC, you saw that the ADC also has an input from the temperature sensor, which is on chip temperature sensor, and we can modulate the ADC control registers so that we can select that channel which is connected to the on chip temperature sensor. So in this third code example, what we are going to do is read the temperature value, convert it in the formula that is given here, recommended in the application note and user manual of MSP430, and the numbers that you get out of that ADC can be directly mapped to the actual temperature. These are the formulas that you have, and once you understand this code, build and download it into MSP430 lunchbox, what you would see is that the display would tell you the temperature at which the MSP430 currently operating at, and you can see the impact of it by trying to cool it, or maybe you connect your your soldering iron gently onto the MSP430 IC, and you should see this temperature reading changing. This is the current temperature when this experiment was being performed. This is the temperature of the IC at that point of time. So I strongly recommend that you go through the codes that 3 codes that have been discussed here. The first one was to read the value of the potentiometer and change the duty cycle of the LED connected on P1.6. In the second code example, we took the value coming out from the potentiometer, but instead of manipulating anything else, we started displaying it on the LCD. And in the third code example, what we did was we took the instead of reading the voltage from external source, we used the internal temperature source to feed the ADC, converted the value, applied these equations to convert the numbers into temperature, and then printed the value onto the LCD display. So, this will give you a brief outline and idea about how to use the ADC and how to convert analog voltages connected to the ADC input of the MSP430 and use them in any which way. Now, one very important point I want to make here is that in many of the cases that you have here, let me draw a block diagram. So, here is your source of analog voltage, which could be a microphone, or it could be a temperature sensor, or it could be any other source. You should not connect, let us say this is your MSP430. Let us say this is the ADC input. It is not recommended that you connect the output of this source directly. The reason being, depending upon the rate at which the source voltages may change, although you are saying that your sample and hold is going to hold the value, it is still recommended that you incorporate a filter, a low pass filter in this, and this low pass filter is often called anti-aliasing filter. Such that the conversion rate that you hope to have with your ADC, the input source remains much lower in frequency compared to the conversion rate. And in our previous examples, because the input voltages are not changing that fast, we did not incorporate such an anti-aliasing filter, but an anti-aliasing filter is nothing but a low pass filter which you can make out of the using R and C, and the requirement is that this filter will be much less than half the conversion rate. So, to take an example, suppose your ADC is going to convert at 10,000 samples per second. Now, because of the Nyquist rate, we require that the input to the ADC should never, the frequency of the input that is connected to the ADC input should never be more than 5000 hertz, 5000 times a second, it should not change, and therefore, this filter should, the low pass filter should have a bandwidth of 5 kilohertz, less than 5 kilohertz. So, the input should never exceed that. So, you should always include a low pass filter to serve as an anti-aliasing filter. In our case, since the inputs that we saw, a potentiometer or an internal temperature sensor, it is not going to change so fast because we are converting the ADC at a much higher rate. Therefore, we are not bothered about having an external anti-aliasing filter, but wherever you expect that the input frequency could go higher, you need to remove those elements from the spectrum, so that the ADC can perform as per the Nyquist rate. So, having an anti-aliasing filter is very important, and I hope that in any application where you expect the input source to have a component which is exceeding the Nyquist rate, that you would cut down the source using a low pass filter to conform to the Nyquist rate. So, I hope that this lecture has introduced you to the great feature of 10-bit ADC that we have on MSP430. It offers so many input channels. It also has an internal temperature sensor as an input to the ADC, an internal resistor divider which allows you to read the supply voltage that is available on the MSP430 that powers the MSP430. You can read that through the ADC. I hope you will play with the ADC features and find how many various ways external signals you can convert using the ADC of MSP430. In one of the next lectures, we are going to not only look at some applications of the ADC by converting voltages being produced by thermistors, but we are also going to use the ADC as a mechanism to give us random numbers or at least a seed for a random number. We are also going to consider how MSP430 can be programmed with additional hardware to produce analog voltages. In this case, we have seen how MSP430 can read analog voltages, but we also need to generate analog voltages. We already seen one mechanism which is using the PWM and low pass filter, but we will see additional mechanisms by which we can generate output analog voltages. So, I will see you very soon in a new lecture. Thank you. Bye bye.